Hi everyone. In this video, we are going to study basic concepts of probability. Let us define probability. Probability is a measure that is associated with how certain we are of outcomes of a particular experiment or activity. An experiment is a planned operation carried out under controlled conditions. Random experiment is an act whose outcome cannot be predicted with certainty. For example, tossing of a coin is a random experiment. Though we know that the outcome of the experiment will result either head up or tail up, we cannot certain what it will be. Other examples of random experiments are rolling a dice and football game. A result of an experiment is called an outcome. An event is any combination of outcomes. Uppercase letters like A and B represent events. For example, if the experiment is to flip one fair coin, event A might be getting at most one head. The probability of an event A is written P of A. Another example, in the random experiment of rolling a die, coming of one is an event. Coming of two is the other event. And coming of even number is another event. The first two events are called simple events because they correspond to only single outcome. Coming of an even number is called a compound event because it corresponds to more than one outcome of the experiment, namely 2, 4, and 6. We can combine events to form new events using the various set operation. The first one is A, U, B, and this is read as A union B. A union B is the event that occurs if and only if A occurs or B occurs or both. This is sometimes called OR event. For example, let event A, whose outcomes are 1, 2, 3, 4, and 5, and event B, whose outcomes are 4, 5, 6, 7, and 8. A union B equals 1, 2, 3, 4, 5, 6, 7, and 8. Notice that 4 and 5 are not listed twice. The second operation is A inverted U B. This is read as A intersect B. A intersect B is the event that occurs if and only if A occurs and B occurs. Sometimes this is called AND event. For example, let A be an event whose outcomes are 1, 2, 3, 4, and 5. And event B whose outcomes are 4, 5, 6, 7, and 8. A intersect B equals 4 and 5. And these are the outcomes that are common to event A and event B. The third is A complement, and we read this as complement of A. This is the event that occurs if and only if A does not occur. Sometimes this is denoted by A apostrophe and read as A prime. For example, let S be an event whose outcomes are 1, 2, 3, 4, 5, and 6. And let A be a subset of this set S, and the elements of event A are 1, 2, 3, and 4. A complement is an event whose elements are 5 and 6. This A complement has elements of set S that are not element of set A. The sample space of an experiment is the set of all possible outcomes and is denoted by S. Examples: number 1. In tossing a fair coin, the sample space is S equals H and T, where H equals head and T equals tail are the outcomes. Example 2. In tossing two fair coins, the sample space is S equals HH, HT, TH, and TT. Example 3. In rolling a die, the sample space is S equals 1, 2, 3, 4, 5, and 6. In throwing two dice, the sample space is given here. The sample space starts with 1, 1 and ends up into 6, 6. Example 5. In a pack of cards, there are 4 suits, which are hearts, clubs, diamonds, and spades, and 13 cards for each suit, that is, from ace through king. There are 52 outcomes in the sample space. Each element of sample space is called sample point. Example: in rolling a die, sample space S equals 1, 2, 3, 4, 5, and 6. Number 4, that is the number 4, is a sample point. Let us define equally likely experiment. Equally likely means that each outcome of an experiment occurs with equal probability. Example: if you toss a fair coin, a head and a tail are equally likely to occur. Let us define mutually exclusive events. A and B are mutually exclusive events if they cannot occur at the same time. This means that A and B do not share any outcomes. Example, let event A has elements small a, small b, and small c. Let event B, whose outcomes are 2, 4, and 6. We say that A and B are mutually exclusive events such that A intersect B equals 0. Hi everyone. Today we're going to study classical definition of probability. The probability of happening of an event E is defined as the ratio of the number of outcomes favorable to the event E to the total number of outcomes. In symbol, this is P of E equals the fraction whose numerator is number of favorable outcomes over the denominator total number of outcomes, or we say sample space. In symbol, this is equal to the number of outcomes for E over the number of the sample space. Let us have example 1. A die is rolled once. Write the sample space and find the probability of letter A. Number 3 is shown up. Letter B, getting an odd number. Letter C, getting a number greater than 4. Letter D, getting prime number. We have a picture of a die on top of our screen. In rolling a die, the sample space is S equals, the elements are 1, 2, 3, 4, 5, and 6. And then, let us write our formula. The probability of event E equals the number of favorable outcomes all over the total number of outcomes. Let's begin with problem A, that the number 3 is shown up, and we write P of 3. In our sample space, we can see that there is only one element of 3. So we write here 1 all over the total number of outcomes is 6. So the answer here is 1 over 6. And this answer we will write opposite problem A. Let us go now to problem B. The probability of getting an odd number. So we write P of odd. In our sample space, we can see that there are 3 odd numbers, namely 1, 3, and 5. So we write here 3 in the numerator over 6 as the total number of outcomes. And this 3 over 6 can be simplified into 1/2. So our answer for the probability of getting an odd number is 1/2. Let us copy this answer opposite letter B. Then let us proceed to letter C. The probability of getting a number greater than 4. So we write here P of greater than 4. In our sample space, there are two numbers that are greater than 4, namely 5 and 6. So we write here 2 over 6. And then to simplify, this is equal now to 1 over 3. And this answer we will write opposite letter C. There we go. Then let us proceed with problem D. The probability of getting prime number. So we write P of prime. In our sample space, there are three prime numbers, namely 2, 3, and 5. Remember, prime numbers are numbers greater than 1 whose factors are 1 and itself. In our solution, we write 3 in the numerator over 6. And when we simplify, this is equal to 1 over 2. Let us copy this answer opposite letter D. There we go. So we are done with our example 1. Let us go to example 2. A jar contains 3 red marbles, 7 green marbles, and 10 white marbles. If a marble is drawn from the jar at random, what is the probability that this marble is letter A, white, letter B, red, letter C, blue? Step 1, let us compute for the sample space. So we add 3 for the red marbles plus 7 for the green marbles plus 10 for the white marbles. And this is equal to 20. And then let us write our formula, and it is now written here. Let us begin with our first problem to get the probability of white. And this is equal to, in the numerator, we write 10 because there are 10 white marbles over the total number of outcomes, which is 20. So this is 10 over 20. And the simplest form is 1 over 2. This is our answer. Let us copy this opposite problem A. Let us proceed with problem B. To get the probability of getting a red marble, so we write P of red. This is equal to 3 because there are 3 red marbles all over the total number of outcomes, which is 20. And this 3 over 20 is already in simplest form. So we will just copy this opposite letter B. Let us proceed now with problem C. What is the probability of getting a blue marble? Getting a blue, this is P of blue, equals 0 because there is no blue marble in the jar as given in the problem. So this is 0 over 20 and simplified into 0. It means it is impossible to get the blue marble inside the jar. So we are done with our example 2, and this is our final answer. Let's proceed with example 3. In a deck of cards, find the probability of getting a letter A, queen, letter B, diamond card, Letter C, black card. In our sample space, there are 52 cards in a deck of cards. Our formula is given, and let us proceed now with our problem A. To get the probability of getting a queen. In a deck of cards, there are 4 queens. So we write here 4 over the total number of outcomes, which is 52. So this is 4 over 52. Then to simplify, this is equal now to 1 over 13. This answer, we will write opposite letter A. Then let us proceed with problem B. Finding the probability of getting a diamond card. So we write P of diamond card, and this is equal to, in the numerator, we write 13, because there are 13 diamond cards in the deck of cards. So this is 13 over 52. And when we simplify, this is equal now to 1 over 4. This answer, we will write opposite letter B. And then let us now proceed with letter C. Finding the probability of getting a black card. So we write P of black card. This is equal to 26. When we say black card, it means the group of clubs and the group of spades combined. So that is 13 plus 13. So in the numerator, we write 26 all over the total number of outcomes, which is 52. And then let us simplify this, reduce to lowest term, and this is equal to 1 over 2. And this answer, we will copy opposite letter C. We are done with our example 3, and this is our final answer. Hi everyone. Today we're going to study elementary theorems of probability. Let us have theorem 1. The probability of the impossible event is 0. In symbol, we write P of impossible equals 0. As an example, a jar contains 10 red marbles. If a marble is drawn at random, what is the probability that this marble is blue? We write the formula for the probability, and that is the fraction, and the numerator is the number of favorable outcomes over the denominator, total number of outcomes. So we write here P of blue, and this is equal to, the numerator is 0 because in the problem there is no blue marble inside the jar, over the denominator, which is 10. There are 10 red marbles in the jar. And to simplify this, this is equal to 0. This is our final answer. Let us have theorem 2. The probability of a certain event to happen is 1. In symbol, we write P of certain equals 1. As an example, a jar contains 10 red marbles. If a marble is drawn at random, what is the probability that this marble is red? Again, let us write our formula. Probability of an event equals the number of favorable outcomes over total number of outcomes. And we write P of red. This is equal to, the numerator is 10 because there are 10 red marbles in the jar, over the denominator is 10 also. And when we simplify, this is equal to 1. This is our final answer. Let's go to Theorem 3. The probability of the complementary event A' of event A is given by P of A' equals 1 minus P of A. Recall that the complement of the event A, denoted by A', is the set of outcomes in the sample space that are not in A. Let's have an example. The probability that Muhammad will pass his statistics course is 0.86. What is the probability that he will not pass his statistics? The probability of passing is 0.86, and the probability of not passing is what we want to know. Our formula, P of A' equals 1 minus P of A. We may write here now the probability of not pass equals 1 minus the probability of pass. And we substitute the value, the 0.86, in the probability of passing. And let us simplify 1 minus 0.86. This is equal to 0.14. This is the probability of not passing. This is our final answer. Let us now define some terms. The first is independent events. Two events, A and B, are said to be independent if the occurrence of one event does not affect or influence the occurrence of the other event. Example 1. A basket contains 7 red balls and 5 blue balls. Suppose a ball is drawn and replaced, and another ball is drawn. If event A is drawing a red ball and event B that of a blue ball, then A and B are independent. Example 2. Toss a coin and roll a die simultaneously. Let A be the event of getting a head, and event B be that the number 4 occurs. Then A and B are independent. Let us define now dependent events. Event B is dependent to event A, such that knowing event A occurs changes the probability that B occurs. Let's have an example. Event A is pulling a king out of deck of cards, and card not replaced. Event B, pulling a queen on the same deck of cards. We say that B is dependent to A because the probability of getting a king is equal to 4 over 52. There are 4 kings in a deck of cards, and 52 is the total number of cards. For event B, pulling a queen on the same deck of cards, the probability is P of queen equals 4 over 51. There are 4 queens in a deck of cards, and the 51 is the total number of cards in a deck of cards, assuming that the first card is not replaced. Hi everyone. In this video, we are going to study basic rules of probability. The first one is multiplication rule, and the second is addition rule. Let's begin with multiplication rule. According to multiplication rule, if A and B are two events defined on a sample space, and if A and B are independent, then the probability of A and B equals P of A times P of B. Let us have an example. In drawing 2 cards in succession in a deck of cards, find the probability that these cards are both aces, given that, letter A, first card is replaced back. Letter B, the first card is not replaced. First, let us write our formula here. The P of A and B equals P of A times P of B. Let us begin by solving problem A. We may write here the P of A's and A's equals P of A's times P of A's. But in letter A, the first card is replaced back after drawing. So when we take the probability of the first ace, we write 4 over 52. There are 4 aces out of 52 total sample space. And when we simplify, this is equal to 1 over 13. Let us take the probability of the second ace. And this is P of A's equals, again, this is 4 over 52. Remember, we replaced back the card, and when we do that, there is still a total of 4 aces. And then, there will be a total of 52 sample space. And when we simplify this 4 over 52, it will be 1 over 13 also. Now, using our formula here, let us now substitute the values. So this is equal to 1 over 13 times 1 over 13. And the product is 1 over 169. We know that we multiply numerator by numerator, and that is 1 times 1 is 1. Multiply denominator by denominator, 13 times 13, and that is 169. So the probability is 1 over 169. And this answer we will write below problem A. Let us now solve for problem B. This time, the first card is not replaced. Taking now the probability of the ace on the first draw, we will have 4 over 52. We know there are 4 aces over 52 sample space. So let us simplify this into 1 over 13. For the second ace, since we are not replacing back the first card, we will have 3 over 51. We assume that 1 ace is taken in the first draw, so there will be 3 aces left in the deck of cards. And in the denominator, it will be 51. So that is 52 minus 1. We subtract the first card that we draw in the first event. So the probability of the second ace is 3 over 51. And when we simplify this, we will have 1 over 17. So let us substitute these values in our formula here. So we have 1 over 13, that is for the first ace, times 1 over 17 for the probability of the second ace. And the product is 1 over 221. And this answer we will write below letter B problem. We were able to write the answers for our example, and we are done with this. Let us go now to addition rule. According to addition rule, if A and B are defined on a sample space, then the probability of A or B equals the probability of A, this is P of A, plus the probability of B, we can see that this is P of B, minus the probability of A and B. Now, if A and B are mutually exclusive, it means there is no common with the A and B. Thus, the probability of A and B is 0. In our formula here, this portion here becomes 0. Thus, the formula will be simplified into this. The P of A or B equals P of A plus P of B. Let us have an example. In a deck of cards, find the probability of drawing letter A, a king, or an ace. Letter B, a heart or a face card. Let's start with our problem A. Let us write our formula here. The P of A or B equals P of A plus P of B minus P of A and B. But drawing a king or an ace is a mutually exclusive event. It means the formula will be simplified into like this. P of A or B equals P of A plus P of B. It means to say, we can write now that this P, A or B is now P of king or ace. And this is equal to the P or probability of king plus P of ace, the probability of ace. So we write 4 over 52 for the P of king. We know there are 4 king cards in a deck of cards. Plus the P of ace, we write also 4 over 52. There are 4 aces in a deck of cards. And then, when we simplify, we can see that the denominators are the same. So we can operate the numerators. 4 plus 4 will be 8 over the same denominator, 52. And when we simplify this, it is now equal to 2 over 13. We divide the numerator and denominator by 4. And this value, 2 over 13, we will write in here. So the probability of a king or an ace equals 2 over 13. Let's go now to problem B. Let us take the probability of drawing a heart or a face card. This is not a mutually exclusive event. So we may write now, using our formula here, that this is P of heart or face equals P of heart plus P of face minus P of heart and face. So let's begin with the probability of heart. There are 13 cards with hearts. So that is 13 over 52 plus the P of face. You can see here there are 12 face cards in a deck of cards. That's why this is 12 over 52. Then minus the P of heart and face. There are 3 cards here, heart and a face at the same time. So we see here 3 over 52. Then let us simplify the fractions. We can see that the denominators are the same. So we can write the numerators 13 plus 12 minus 3 all over the same denominator 52. When we simplify the numerator, it will be 22 over 52, which is reduced to lowest term as 11 over 26. And this value is our probability of drawing a heart or a face card. And we put our answer below problem B. We are done with our example here. This is our final answer. Today we're going to study probability using permutations and combinations. Many interesting probability problems involve counting principles, permutations, and combinations. In these problems, we will use permutations and combinations to find the number of elements in events and sample spaces. These problems can be complicated, but they can be made easier by breaking them down into smaller counting problems. Let's have example 1. A bag contains 3 red balls and 5 black balls. 2 balls are drawn at random from the bag. What is the probability that the balls drawn are both red? The formula for probability, we know that this is a fraction, where the numerator is the number of favorable outcomes, and the denominator is the total number of outcomes or sample space. Let's begin with our numerator, that is the number of favorable outcomes, and based on our problem, this is a combination of 2 red balls out of 3. The formula for combination is here, and we can now change this into the C of 3, this is the N, comma 2, and the 2 is our R. And this is equal to 3 factorial over the quantity 3 minus 2 factorial times 2 factorial. Let us simplify the terms inside the grouping symbol. The 3 minus 2 is now 1 factorial. Simplifying further, our 3 factorial can be written as 3 times 2 times 1. And 1 factorial is simply 1. While the 2 factorial is 2 times 1. We can cancel the number 2 in the numerator and in the denominator. So simplifying the numerator, we have 3 times 1, which is equal to 3. And the denominator becomes 1 times 1, where we can simply ignore our denominator because it is equal to 1. So the final answer is 3. It means the combination of 3 taken 2 at a time is equal to 3. And this number 3, we will substitute in our numerator. There we go. Now, let us go to solve the total number of outcomes or the sample space. Based on our problem, the sample space or the total number of outcomes is the combination of 2 balls out of 8 total balls. The formula of combination is here, and let us substitute the values. So this is C of 8, 2 is equal to 8 factorial over the quantity 8 minus 2 factorial times 2 factorial. Simplifying further, this 8 minus 2 becomes 6 factorial. And then, let us now expand the factorial. The 8 factorial in the numerator can now be written as 8 times 7 times 6 factorial. While in the denominator, the 6 factorial, we can leave it as is, and we will expand the 2 factorial into 2 times 1. The 6 factorial in the denominator can now be cancelled with the 6 factorial in the numerator, while the number 2 in this denominator can be cancelled out with the number 8 in the numerator, and this number 8 becomes 4. Now let us simplify. The numerator becomes 4 times 7, and that is 28. While in the denominator, everything is cancelled, while there is number 1 here, and that 1 can be simply ignored. So the final answer is 28. So the combination of 8 balls taken 2 at a time is 28. This is our total number of outcomes that we can substitute in the denominator here. So we have our answer 3 over 28. This is the probability that the balls drawn are both red. Let us have example 2. A 4-digit pin is selected. This PIN means personal identification number. What is the probability that there are no repeated digits? The formula for probability is here. So let us begin solving our numerator, the number of favorable outcomes. Based on our problem, this is the same with permutation of 10 digits taken 4 at a time. The formula of permutation is here, P of n, r equals n factorial over the quantity n minus r factorial. And we can write this to be P of 10, 4. And this is equal to 10 factorial over 10 minus 4 factorial. This 10 minus 4 can be simplified into 6 and the factorial is still there. So we have now 10 factorial over 6 factorial here. Expanding the factorial in our numerator, we can write 10 times 9 times 8 times 7 times 6 factorial. We can stop in the 6 factorial because we can see that there is a 6 factorial in our denominator. So we can now cancel both the 6 factorial in the denominator and in the numerator alike. And then let us get the product of 10 times 9 times 8 times 7. And the answer is 5040. This value is our numerator and we can substitute it there. So there we go. Now let us solve for our denominator, the total number of outcomes. And this time, we can see that it is a permutations of 10 digits taken 4 at a time and repetition allowed. In this case, we're going to use the multiplication principle or the counting principle. Thus, permutation can be solved by writing first 4 blanks to represent the 4 digits. Also, the 4 blanks is the number of stages where each stage we will write the number of choices. It means in our first blank here, we're going to write the number of choices. We have 10 digits from 0 to 9. So it means in the first blank, we have 10 options. On the second blank, also, we have 10 options because repetition is allowed. On the third blank, there will be 10 options also, the same way with the fourth blank. So we have here 10 times 10 times 10 times 10. And this is 10,000. And this value is our denominator, the total number of outcomes. So let us substitute. There we go. So our answer here is 5040 over 10,000. This is the probability. Now for the fraction, we can simply reduce this to lowest term, and this is equal to 63 over 125. This is our final answer.